next session, which is a pre-recorded session by Mohammed, and it's a simulation framework for critical infrastructures subject to natural disasters. So Nicholas, you can...
Hi, good day. My name is Mohammed, and I will be presenting a simulation framework for control critical infrastructures subject to natural disasters. The associated authors are Craig Ramlal, Arvind Singh, Sean Rock, and Daniel Goicha. The objective for the research: the development of a simulation framework to evaluate natural disasters imposed on critical infrastructures using the Infrastructure Interdependencies Simulator Toolbox. The sub-objectives: the development of a simulated disaster test environment, development of appropriate testing procedures to analyze the effects of natural disasters on critical infrastructures, development of heuristic controls for controlling resource allocation in disaster scenarios, and lastly, the generation of disaster policies for different disaster scenarios. I'll now discuss an introduction or give an introduction to IZSIM. IZSIM is a platform which allows for the analysis of interdependent behavior of interconnected infrastructures under different operational constraints. The IZSIM toolbox was used to break down large complex systems into simple components and allow for modeling critical infrastructure in a modular and flexible manner without taking details into account. Each cell within IZSIM contains 5 physical modes which model the input-output relationship for different operational scenarios when the cells are subjected to a natural disaster. Essentially, the IZSIM toolbox is a tool that was used to help facilitate the simulation of critical infrastructures that helped us generate the results which we will be presenting shortly. The model overview are the model elements, and the model elements are the elements that are used within the simulation to help generate the results, which we will discuss now. The first being the production cells. The energy and water production cells are the resources or the 2 main inputs into the simulation or into the system. Then we have the resident cells. These are used to simulate the population size in a given area. The health facilities. The health facilities were used to simulate the behavior of treatment facilities given a disaster scenario. And lastly, there was the aspect of debt. Debt was a metric which was used to determine the best possible outcome for a given disaster scenario. So it helped with the decision-making process. And that was recorded as an iterative collection of failed treatments. The model or typical community, this figure here, which is figure 1, shows the model outline or the general model that was built and simulated. In the model, we have an energy distribution system that sends energy to loads A to G. We have 7 loads. Each load consists of different cells, in some cases a health center and a resident cell. In this case, load D has a resident cell alone. And for loads E, F, and G, we have different residences with associated pumps. In this case, we have pump 1, pump 2, and pump 3. The blue line that goes from the pump to the different loads shows the water distribution system for each of the pumps. The testing procedure for the energy production cell. The testing procedure conducted on the energy production cell involved the exhaustive evaluation of the effect on the model for each combination of physical mode values. The testing procedure that we used was a rotating blackout, or what is also known as the rotation of loads. The rotating blackout was a specific situation in which loads were turned on and off for a specific period of time. At each simulation iteration, unique combination of physical modes was simulated with the controller reporting the best combination of rotation of loads. Figure 2 shows the heuristic controller for the energy production cell. It's essentially a flowchart which describes the control method for evaluating the best possible outcome based on the physical mode that the energy production cell is currently in. The testing procedure for the water production cell. The testing procedure was broken up into 2 different scenarios. The first being 1 pump damage scenario, which involved all combination which involved only 1 pump being damaged, and the second scenario, which was the 2 pumps damage scenario, which considered all combinations which involve only 1 pump being undamaged. We will also present 2 relief methods, the first being the movement of people, which was implemented as a relief method in which sickly from an overcrowded health unit was moved to another health unit that was not overcrowded, and the truck-borne supply strategy, which was also a relief method in which water resources were delivered to cells anywhere in the model. So these two relief methods were used with the testing procedure to show the effects of the relief method and how it affects the debt. This will be presented when we get to the results shortly. Figure 3 shows the heuristic controller for the water production cell. It's essentially a flowchart which describes the control method for the distribution of water based on the physical mode that the water production cell is currently in. We will now discuss the results for the energy testing. Table 1 shows the rotation of loads for physical mode 2. The table shows the various combinations that can be turned on, and from the table you can see that there are 7 different combinations. It has the associated water resources for each of the combinations, as well as the debts recorded for each of those combinations. The situation was re-simulated with a relief strategy known as the movement of people, and you can see the changes in debts before and after when the relief method is used. Table 2, similar to that of Table 1, shows the rotation of loads for physical mode 4. It shows the different combinations that can be on. In this situation, we have 5 different combinations. We have the associated water resources for each of the combinations and the debts recorded for each of those combinations. And similar to that of the last table, we simulated the movement of people relief method to show the variation in the debts before and after when this method is implemented. We move on to the results for the water testing. Table 3 shows the comparison of results for when one pump was damaged. To the extreme left of the table, it shows the variation in the physical mode, and the table is partitioned into 3 different parts. The first is considered for when pump 1 is damaged individually. The second is for when pump 2 is damaged individually, and the third is for when pump 3 is damaged individually. For each of the tables, you can see the cyclic generated, the total debt generated, as well as what happens when the movement of people relief method is implemented and how it affects the situation. The color scheme just shows the criticality levels for each of the physical modes for each of the pumps. Table 4 shows a comparison of results for when 2 pumps was damaged. So based on the time and the considerations for the presentation, we decided to use an example scenario. In our example scenario, we consider when pump 2 and pump 3 is damaged simultaneously while pump 1 is undamaged. So you can see the cyclic that is generated, the treatment rate for each of the associated cyclic, and the total debt that is generated for this specific situation. We were able to show the relief methods or re-simulate the situation with the relief methods and show where the relief methods can be implemented for each specific situation and how the debts are recorded. We will now discuss the energy production policies. It is evident that loads E, F, G, which contain a water pump, must be given highest priority as a result of cascaded failures seen by dependent cells. Results show that when cells are off, there is still a minimum operational capacity achievable if water is provided to the cell. In situations where less loads can be turned on, for example at physical mode 4, the combination of loads which generated the lowest number of deaths when on were loads A, E, F, and G, and loads B, E, F, and G. However, the movement of people relief method can be adopted to reduce the debts further. Restoration of energy services should be prioritized based on the following table to achieve the most optimal impact. So table 5 shows the inferred prioritization of loads based on the load dependencies. In this table, priority 1 represents the highest priority, and priority 5 represents the lowest priority. The priorities are dependent on the number of cells affected as well as the number of loads, which you can see in the table as shown. And this is a scheme that was developed based on the results that were generated. Water production policies. It was evident from the test scenarios that pump 3 was the most critical pump, followed by pump 2 and then by pump 1. Therefore, in the event of a disaster, the restoration for these pumps should be prioritized in that order. Relief methods such as movement of people or the truck 1 supply should therefore be allocated given preference to the dependent cells in conjunction with the pump prioritization previously stated in order to achieve the most optimal response. In conclusion, in this study, a simulation and control framework was developed for evaluating response decision policies for natural disaster scenarios, aiming at reducing the loss of life. The framework targets water and electricity utilities and produces recommendations for the best possible decision to reduce the casualty count for each disaster scenario. The framework has put forward a testing approach which aims at looking at all possible disaster situations which would be difficult to investigate under real-life conditions. I would like to thank you all for listening to the presentation. If you all have any questions, feel free to email us at any of the listed emails, and do have a wonderful day. Thank you.
Okay, thanks very much, Amir. Right. Unfortunately, Amir and these authors are not available with us, and we have some questions that we can take offline and send it to them. And so I